So, hey everybody, thank you all for coming. I hope that you grabbed the beer and pizza and you enjoyed it. And today we're going to talk about deep analysis of Clickstream. Now, first allow me to introduce myself. My name is Segev Arbiv. I'm a data scientist here at SimilarWeb, part of the amazing data analysis group. I currently now live in Tel Aviv after many years, or too many years in the Technion, where mostly my focus was on computer vision, the classic one, machine learning, and I dealt in my career also in the deep learning and now with NLP. So a bit about what we're going to do today. So Einat told you about SimilarWeb, so we already know. So I'm just going to talk about some problems that we are facing regarding the privacy in the digital world. And how looking at URLs as a language actually helped us to tackle it and get even more insights that allowed us to classify the web traffic. And eventually we're going to do a short summary of everything. So privacy in the digital world. Now, I'm sure that you're all aware about the GDPR, the new data policy, the data privacy regulations that came last May. And I'm sure that you all see a lot of terms updates and data policy updates from the various products that you are using. Now, this is really reshapes the way that the data is handled around the internet. And SimilarWeb, as being a GDPR-compliant company, will continue to ensure that our users' privacy is protected and no personal information is being used. Now, in our world, it means that the clickstream, our data, mustn't contain any PIIs in our URLs. Now, a PII is a personally identifiable information, actually information in the URL that can lead back to a specific user. Here you can see some examples of PII. So for example, the first link, this is the URL to my LinkedIn profile. You can see my name and surname. Now, if you will click on it, you will get to my social media page, and you will actually have access to a lot of information about myself, making me not anonymous anymore. The Facebook, if you will click on that link, you get the Facebook ID over here. And if you will click on it, you will get to a Facebook image. This is Mark Zuckerberg's profile page. And again, now you have access to all of his profile, which again is no longer anonymous. And we said that we can't use, and we're not using any URLs that contain any personal information. This is not what we care about. So we want to stay the GDPR compliant. Now, as you can see, some parameters are really identifying what's happening here, right? The email, name, and surname. So the current method, some methods use rule-based heuristics in order to find those PIIs. But those parameters are constantly changing, especially in the dynamic world of the URLs. So we wanted to see if we can extract more information from the URL itself in order to tackle this problem. So we moved forward to look at URLs as a language. Now, what can we learn from URLs? Unlike traditional languages, URLs lack the semantics, grammar, and clear separation to part of speech, right? In language, we have noun, verbs, adjectives, and in URLs, it's not so clear. But actually, URLs do serve as kind of protocol for transferring information around the web, right? So it actually is kind of a language. So maybe we can get a numeric representation of that URL after any splitting into words or somehow. And while getting that numeric representation, we can apply any NLP techniques on it in order to properly classify, in this case, the PIIs that we've seen in the URLs. So now, in order to do that, I'm just going to do a quick review on what is a generic NLP flow, which I'm sure that you all know, right? Usually we have our corpus, right? Here it's 3 sentences. PyData ranges awesome meetups, meetups are cool, and cool meetups are PyData specialty, right? All right, great. Now, in our case, it's just going to be millions over millions of URLs that we need to build the corpus from them, right? So the next stage usually is going to be building the vocabulary. The vocabulary is just a simple mapping between each unique word from the corpus to an index, right? So this is the first stage of getting the numeric representation of our URLs. So the next step is just going to be an auxiliary step, map each of the sentences to the set of the indices that composes the sentence, right? So PyData, I'm going to the vocabulary, it's ID number 1, so I'm putting 1 there, and meetups number 4, and so on. You got the point, right? Yeah. So how I'm actually getting the numeric representation? So I'm going to use something that you all know. This is the embedding matrix. Now, an embedding matrix is just a matrix that maps for each word in a vocabulary a vector in the size of k that represents her. This is the numeric representation. So now, for example, PyData, which is mapped to ID number 1, it's represented by the k-length vector in the first column of the matrix. Awesome is represented by the vector in the third column. Is that clear? Right, we all know that. So usually this is either randomly initialized, or we can use any one-hot encoding, or if we have any pre-trained word embeddings like word2vec, we will use them. Now in our case, we're talking about URL, something that we haven't seen before and doesn't possess any pre-trained word embeddings. And this is actually, it's a very important intermediate because this is constantly updating during training the model. Right? The vectors are being updated to get a more meaningful representation of the words. So the last step is just going from the indexing part and get the numeric representation for each sentence. So vector number 2 arranges, I'm going to column number 2, maps it to the k-length vector, and now I have a numeric representation for each of the sentences. So how can we apply it on URLs? So let's say that we have this Wikipedia page, and I want to get a numeric representation for it. So if in the normal language we would split or tokenize the URL by the sentence by commas, spaces, and dots, here I can do actually tokenization by special characters, dots, backslashes, question mark, and so on. And I'm actually getting the words that composes this sentence or the URL in comparison. Now, if I will do it on all the URLs, on all of my corpus, I can actually construct my vocabulary, right? And I have that vocabulary. I can get the word ID for each one of those words. And again, I constructed already an embedding matrix in the size of the vocabulary, which is now randomly initialized. I can get a corresponding vector for each one of the word IDs. And eventually, I'm getting a matrix representation of that URL, which I can use any data, any statistic tool on top of it to do any kind of classification tasks or any NLP problems. So let's talk about a bit NLP and its pros and cons. Now, classical approaches for text classification like bag of word or extracting any lexical features have many drawbacks. The first one is that usually we have too many words in our vocabulary, which can result in memory constraints while we train the model and getting the word embedding. Especially in our world, in the URLs, when we have thousands new URLs every day and in multiple languages, keeping such matrix is not feasible, right? Because we're going to need a constant size matrix, which can't happen here. Now, the second problem is new word at test time. I can only obtain word embeddings for words that I've seen before, that actually have been in my vocabulary. So infrequent words or new words at test time actually get the unknown token, which I'm sure that some of you actually heard of it. A word that you haven't seen before, you cannot get the embedding for it. And it usually requires expert feature engineering. In language, we get linguistics to help us construct those features. In URLs, we can think about statistical features like the length of the URL, the number of dots in the URL, and the length of every segment in the URL, which can be very time-consuming. On the other hand, convolutional neural nets have recently shown promising performance on text classification. And I want to talk about one in particular. So this is URLNet. URLNet is a CNN-based model for malicious URL detection. It's a paper and a work done by Hang Li et al. At the University at Singapore. It actually represents URL using two branches, the word level embedding and the character level embedding, getting the representation from each branch and actually apply a CNN on each one of them, and eventually they are combined into one. Now let me dive further into this. So let's say that I have M words in my vocabulary. So I have the corpus of the URLs, I did tokenization by special characters, and eventually I have M words in the vocabulary. And I have C unique characters. Now C is finite, right? You have the ABC, you have dots, backslashes, question marks, all the characters that composes URLs. And let's say that I want to represent each word or character in a vector of length k. Again, this k is a hyperparameter that can actually be changed after. So what URLNet does, it represents the URL in two different branches. The character level, or the character branch, takes the URL, split it into characters, right? We have C number of characters, get the corresponding vector that represent the character. And eventually we'll have a matrix representation that will represent the URL in the character level. Now, in order to do that, we need the first embedding matrix, the character embedding matrix, that maps each character to a k-length vector. And I'm going to show a bit of what I meant. So let's say Amazon.com, right? So the first step will be split the URL into characters. I split it into characters. Now I can go and get their character ID. This is the auxiliary stage that we talked about. And once I have the character ID, I can go to the embedding matrix, the character embedding matrix, and get the corresponding vector for each character. Right? So now I have a matrix representation of the URL in the character level. This is after followed by convolutional layers, and we can see that we're actually trying to find relationships between different characters in the URL, right? Which is usually very helpful. But what it ignores here are the word boundaries, right? It actually also tried to find the relationship between characters from different words. This W and that AM are not necessarily connected to each other. So the paper offers a second branch, which is the word level representation, that will only look at the word level and actually not going to ignore those dots and the separation. So the second branch, as I say, the word level, we've seen it before. You're taking the URL, split it into the words, and get a representation for each word. So this requires the word embedding matrix that maps each word into the corresponding vector. Now, we said at start actually that word level embeddings have a lot of drawbacks, right? I can't infer any new words in test time, and if the vocabulary is so big, I cannot manage with this matrix. So the paper offers a third and final representation matrix that also maps characters to embedding vectors, but this characters is different representation from the first matrix, because this characters only talks about characters that are being in the same word. Only characters that are used in words together will be learned here. And I will show an example in a sec. I just want to emphasize that those three matrices are randomly initialized, right? And they're gonna change and they're gonna update during training using the backprop. So the backprop of this net will also update the weights of the filters of the conv layers, and will also update the embedding matrices here. And by that, we're going to get a more meaningful representation for each character or word. So the word level is actually constructed from two different areas. So if I want to represent HTTPS, for example, the most direct approach will go, as we've seen before, get the word ID, and get the corresponding vector from the word embedding matrix. So now I have a k-length vector that's represented. Now I can go even furthermore, and I can split that word into the characters that composes it. Get the character ID, and then go to the character embedding matrix that find relationships between characters within the same word, and get the corresponding vectors. So now on the right, actually I have a matrix representation of the word in its character level. Is that clear? So if I want to enjoy both of these worlds, I can do a quick summation, right? I'm going to sum on some axis of that matrix, element-wise summing those two vectors from the word embedding and the character embedding. And eventually, this is the word embedding that I'm getting from that word. It's constructed from both character level and word level. So this is done for one word from the URL. So URL itself will give us a matrix, right? So on top of that, we can use, as we said, convolutional filters. And I want to show you some results. What about words that we haven't seen before, right? This is the problem that we want to tackle. So let's say that I'm tackling the word iPhone XS. Now, 6 months ago, iPhone XS as a word around the web didn't existed. So if I would try to get an embedding for that word, I would go to my vocabulary and I would get the unknown token, right? I didn't see it 6 months ago. So now if I want to obtain an embedding for it, it's going to be problematic. So this is where the character level come at hand. I can split the iPhone XS into the characters that composes it, get the character's ID, which I always have because it's finite numbers of characters, and I can get a matrix representation for iPhone XS. Again, after summation, I get a word embedding, a vector embedding for new words that I haven't seen before. So this is how it actually solved that problem of infrequent words that usually we ignore because of the size of the vocabulary, and new words that I haven't seen before at all at test time. So I want to show you some results of their paper. So this is the URLNet architecture. You can see that the first two layers are the embedding layers that we just talked about thoroughly. Those are followed by convolutional layers and fully connected layers, which I'm not going to elaborate on because I think that we are aware about them. And I remind you that their task was to properly classify between malicious URLs and non-malicious URLs. So they actually trained their model, took a vector representation from the last layer of the architecture, and this is the projection of the URLs that, of the results that they got. Now we can see a clear separation. This is a really nice result. We can see clear separation between the non-malicious URLs on the left in green and the malicious URLs in red. Now, moreover, you can see that there are a bit of clusters around the image. So actually, let's say that URLs that have Google as a main domain are in one cluster at the top, at the bottom left, and URLs that have zip file extension are in different clusters, which is really interesting because we can see that the URLNet actually learned and what to emphasize from the URL and it learned the proper representation. So we said, well, that's great. Now, how can we use it? Remember, we said that we need to find PIIs, right? We need to find in the URLs something that can lead back to the user. So actually, we took the URLNet and we retrained it with now the new objective of either the URL possess PII information or doesn't have any PII information on it. So we actually used 2 million URLs, and the URLs had PIIs in the forms of emails, locations, zip codes, and so on. And we actually got 97% accuracy, which for us was really impressive. But moreover, we actually found PIIs in URLs that weren't found during the rule-based heuristics. You can see here that we have the name, surname, and nickname of two users from two big social media. You don't see it in the back. Trust me, there are URLs here with name, surname inside of them that were found in that the current rule-based heuristics didn't find. Now, this is really great. So we could actually generalize and find new parameters and new combination of characters in the new dataset of the URLs that weren't found in the current heuristics. So it was really interesting for us, but it was one task. We actually wanted to expand the usage of URLNet for some other use cases. And I want to take you to the second use case, which is traffic from sponsored links. Companies and industries around the internet really care about measuring how much sponsored traffic they're getting and their competitors getting. This is how they measure the efficiency of their online campaigns. Now, any one of you that did any marketing research recently knows that URL actually possess some parameters that can indicate whether the link is sponsored or not. Like UTM source or UTM campaign are parameters that indicate, yes, this link is sponsored. But actually, any company can decide that it will use different parameters, new parameters that haven't seen before. So we wanted to see if we can actually generalize and learn new parameters, right? Parameters that never seen before. So we wanted to use URLNet to find those indicating parameters. So again, we took the URLNet, we retrained it, and by retraining, I remind you that the embedding matrices are changing according to the task. Before that, the embedding was corresponding for PIIs, and before that, it was for malicious URLs. Now, the character level and the word level embedding will be different because the backprop, it's according to the problem and according to the data. So we retrained the URLNet to find whether the link is sponsored or not, and we did a projection of our results. And this is quite interesting. We see that the sponsored URLs are clustered right in the middle in a very nice way, and the non-sponsored URLs are surrounding it. So there is a nice separation between the two. We actually took it a bit further, and we took the 5,000 URLs from each class where the model was most confident about its answer. And this is what we got. And again, we can see a clear separation. Now, it reminded us of something, but we really couldn't put the finger on what it is, but we felt like it's a good place to stop the training, and we were really happy with the results. Now, great, we saw that one URL possessed enough information for some classification tasks, right? But here at SimilarWeb, we often challenge much harder tasks that require actually a clickstream or a browsing context rather than one URL. So what we did was take a list of URL or a window of URLs and actually fed them into the URLNet, ignoring now the objective function and just taking it as an embedding machine. Now, we took those embeddings and we actually fed it into a sequential model. In our case, it was an LSTM. And now we can actually talk about predictive analytics. And here the possibilities are endless. We can talk about what's going to be the next website that the user will visit, in what category that website will be. Or if you're interested in marketing, right? If you have a commerce site, you care about the conversion rate. What is the likelihood that after a pattern of this kind of usage, the user will buy your product, subscribe to your page, right? So here, the possibilities here are really endless, and this is some of the projects that we are working on and planning on working on. So let's talk about something that we had in mind during the training, right? So we use bidirectional LSTM because we want to find dependencies between URLs from both the past and the future. We had a couple of constellation. We tried a different number of constellation about what is the number of URLs in the window that is needed to generate some insights. And of course, tweaking the neural net parameters of the embedding size, K, that we talked about, the learning rate, and so on. We had also the parameters of the URLNet and the LSTM. So it's a whole bunch of hyperparameters to tune. So let's just summarize what we saw here today. We saw that Clickstream can be seen as the language of the digital world. And we saw how we can get insights, generate insights from it. We saw that deep learning techniques can overcome classical approaches' drawbacks, right? Which is known, but now we can see that it also applies to the URL world. It really reduces the amount needed by expert feature engineering. We saw how character level analysis helped us overcome the infinite vectory, right? The infinite vocabulary, sorry, and how we can get representation for new URLs, new words that never seen before. And we saw that URLNet really provides meaningful representation of URLs for various classification tasks. And most of all, it was fun. I think that as a data scientist, we have the privilege of dealing with some really interesting tasks, and I'm really waiting for the next meetup to show the results of the predictive analytics. And I want to say thank you to the people who worked on this project, Omer Ben Shitrit, Yaniv Katz, and Evgeny Olovich. And it was really nice talking here. Thank you everyone for listening, and if you have any questions, you are more than welcome. I hope that I didn't talk too fast. And thank you. Please. Oh, okay. So she asked how we are dealing with non-English characters in our URLs. The characters like Chinese, for example, Chinese URLs. So that's a great question, and I mentioned it before. We actually are dealing with URLs in various languages. We are dealing with URLs in Russian, in Japanese, and so on. And even those are represented by characters, by finite set of characters. So the character embedding matrix is still something that is trainable. It's not that huge. So if we take that and we took it on various languages, it dealt really well, because eventually Russian or Chinese characters embeds into a specific character ID. We used, in English it was 100 tokens, so if we expand it, it's now 500 characters that composes the URLs in different languages. So it actually dealt in a pretty straightforward way. We didn't have to use any additional information from the URL itself.
Did you use downstairs models, or?
We tried a lot of, it was the same model eventually, but during the process we tried different models from RNN and LSTM, and we didn't need attention. We tried to use attention, but it's only when the window of the URLs was big enough to exploit that advantage. Yeah. 7% doesn't sound enough if you got these. Good questions. Yeah, super. So the first question was, well, the second question was about the 97% accuracy, like the data set is probably skewed, so what we did about that. And the first question was, remind me? The subword embedding. So actually, I forgot to mention it, so thank you. The character level, the third matrix, the character level that look on relationship between characters in the words, this is the one that extracts representation of subwords. I showed the example of the iPhone XS, right? The iPhone XS is a new example, but iPhone and iPhone X is not new. So this is how we could deal with the character level representation of iPhone, right? So iPhone XS representation will not be that far from iPhone XS. And so this is how we use it. Fast text and so on. We didn't use pre-trained word embedding because usually URLs contains a lot of gibberish. And the 97% accuracy, it's true. We looked also about different metrics like area under the curve. The dataset was skewed. There was like 15% PIIs and 85% non-PIIs. But we saw that the false negatives were the false negatives ratio were low. So we said any PII that we have in the data, we only, I think, we've mistaken in 0.08% of the time. So there was some URLs that we said that they were PII when they weren't, but the opposite didn't happen, and that's actually what's important for us. Yeah, please.
You mentioned that you summed the character embedding.
Yeah.
Don't you lose some of the signal?
I agree. I presented the paper. This is their work. I agree, like more on in the idea, right? But the results were different. The results spoke differently. It was really good accuracy, and the ratio and the false positive, the false negative were really low. So I do agree that by summing up, especially like that summation, you lose a lot of information. Moreover, the character level embedding and the word level embedding sometimes may be in different scale. So I think that if you use those, you probably lose some. Practice showed different. So they actually have shown that if you use both analysis, like word level and character level, it's far more superior than use only one of them. So actually it did work, but I share your concerns.
Okay. And in the entire pipeline that shows the prediction, do you train it end to end?
Yeah. The entire thing, the entire architecture is end to end. So the word embedding matrices, the character level matrices, and the weights of the entire convolutional layers and fully connected layers are trained jointly. So I think that a lot of deep learning models, especially in Vision, for example, like faster RCNN and so on, show that end-to-end frameworks usually works better than those that works in two parts. And this is the case also here. Yeah. Okay, so he's asking about the difference between the scale that I said, between the word level embedding and the character level embedding. It's not that different, but if you sum an 8-column vector, 8-column matrix, so it's going to be one magnitude more than the numbers on the word level embedding, right? Let's say that they're all Gaussian distributed between 0 to 1 at first, so this will be 10 times bigger, the representation. But there wasn't any larger difference of scale between the representation of character level and word level. Any more questions? I'm really enjoying standing here, so yeah.
How did you obtain the ground truth for the data set? How did you obtain the ground truth for the data set?
So we had a labeled data set from different kind of resources that we have, that some of them are rule-based heuristics, some of them were tagged by other mechanism, but we had the ground truth in hand. Yeah. So I'm just going to repeat the question and the answer. Did we use any special embedding for the unknown character? The answer is not, and sometimes using zeros perform the same as a random embedding. Yeah. Okay. So the question was, this problem has many ways to tackle it, right? So URLNet is just one of the problems that we are tackling. So what was the difficulties on the road that we encountered?
How long did you do it for?
Well, it took some time. It took some time, but once we got to the model, yeah. So I share with you the link here, and you can see also it's the source code of this thing. we need to do a lot of tweaking. Let's speak about the URLNet. We needed to do a lot of tweaking of the parameters or of the number of the layers of the objective function, right? Because sometimes we didn't want to only classify whether the URL contains PII or not. We wanted to actually rather know where does the PII in the URL itself, like where it starts and where it ends. So it took some time. Now, before that, some heuristics, as I said, included rule-based heuristics. So these are often less sophisticated, let's call it, but actually they are more time-consuming, right? Because here we used a deep learning framework which did the end-to-end feature extraction for us. So most of the time went on how to deploy this thing and how to tweak the parameters and layers and the number of classes in the end, because the embedding matrices, the representation of the characters and the words is explicitly defined by the way, right? So PII will get different embeddings and sponsor link will get different word embeddings and character level, and usually using one embedding from one task to the different task is not going to work. It really learns its own field, let's say. So I hope that answered that. It took time, and but the end-to-end framework really helped us extract the features in a more in a faster way. Yeah. The question was, they compared it to other benchmarks. So the paper, they actually compared it to UCT, which is URL component tokenization, which actually looks and builds different dictionaries for different parts of the URL. For the main, so the main domain will get different embeddings, like .com in main domain and com in just in the URL will get different embedding. Some other techniques like trigrams or bigrams that iterating through the URL. So if they actually took all of the expert features, like, let's call it, and combined them, and this performance was better. So this outperforms all of them in, I think, 8% accuracy, but actually they measured it by area under the curve, so it was some improvement. Yeah, but good question. So thanks, and that's it.